Okay, guys, here's going to be the answer key video for kind of our review for our chapter 1 through 3 test, our first test of the semester. So I'm just going to kind of get through these problems, show you how I would solve them, and hopefully give you some advice if you get, or some starting point if you get stuck on stuff. So if you have any more questions, if you need something elucidated further, please don't hesitate to contact me. And I can certainly explain anything, as in-depth as you need. So I'm going to do this kind of quickly. I'm going to hope to keep the video small enough to mount on Teams and not have to use YouTube, but if I got to use YouTube, I do. So with no further ado, let's get to it. Okay, circle the chemical symbols which are properly written. So for a chemical symbol, we know two things. One, that it has to be either one or two letters, and two, if it is two letters, that the second one must be lowercase. So that would exclude this one because the second letter isn't lowercase. That's a valid symbol, as is that. This one has three letters, so it is not valid. This one, it needs to have a lowercase second letter, so it is not valid. That one is valid, and here any one symbol, one letter symbols, should be capitalized, so that one is not valid either. And we're going to look at this particular sugar molecule here, and a carbohydrate molecule, and we've got C2H8O6. How many hydrogen atoms are present? There are 8. In the total atoms present, there are 6 oxygens, 8 hydrogens, 2 carbons, for a total of 16. And now if I had 7 molecules of this, I would have 7 molecules, and each of those molecules has 6 oxygens, so I would have 42 total oxygen atoms. This compound is covalent. Let's get it on the screen. Because there are no metals present. If I look these things up on my periodic table, carbon is a nonmetal, hydrogen and oxygen are also nonmetals. Since there is no metal present, this must be a covalent compound. Down on the bottom here, how many oxygen atoms are present? So in each one of these compounds, there are 2 groups of nitrates of this NO3 stuff. Each of those have 3 oxygens. So each one of these kind of compound formula units will have 6 oxygens. But now we have 3 of those quote-unquote molecules. This actually isn't a molecule, but it's a formula unit for an ionic compound. But we have 3 of them. Each one has 6 oxygens. Multiplying the 2 by the 3 gives us 6. Multiplying that 6 by this 3 gives us 18, and tells us we would have 18 total oxygen atoms. Okay. How many total atoms are present? Well, we have 6 oxygens, 2 nitrogens, so 8, plus a calcium, so 9. So we have 9 atoms per formula unit. We have 3 formula units, so 3 times 9 equals 27. There are 27 molecules present. Okay. Compound ionic or covalent. As I mentioned, this compound is ionic. This is on the one on the previous page, and that is because this right here, calcium, is a metal. And as soon as we find that there's a metal present in the compound, we know it must be ionic. Pure substance, homogeneous or heterogeneous mixture. I'm gonna, give me just one quick second here, ladies and gentlemen. I'm gonna back out of my email so that we don't get any more dinging like that. I apologize for that. There we go. Okay, now it shouldn't beep. So, pure substance, homogeneous or heterogeneous mixture. Chunky spaghetti sauce is different in different places, so that's heterogeneous. Air is a mixture, but it is the same everywhere, so that is homogeneous. Carbon dioxide is a pure substance. It is a compound. Aluminum foil, now this one's kind of a little tricky. I'm going to say that it's a, I'm going to say it's a pure substance. You could also make an argument that it is truly a heterogeneous mixture because on aluminum foil we make this kind of layer of aluminum oxide on the top and the bottom, and therefore we would have different substances in different places. But that's getting pretty fine-grained for where we're at, so let's just kind of consider it to be a pure substance. Unscrambled eggs are definitely different in different places, making them heterogeneous. Well scrambled, if you scrambled them well enough, you could get them to look the same everywhere, which would be homogeneous, and water is a pure substance that's a chemical compound. For here, solid, liquid, and gas. Solids have a definite volume and a definite shape, it's always known, and they have low energy. Liquids have a definite volume. They do not expand to fit their container, but they do take on the shape of their container. So that's an indefinite, and they have a medium energy. And gases expand to fill their container, so they have an indefinite volume. They also take on the shape of their container, so they have an indefinite shape, and their energy level is high. On the periodic table, columns are called groups or families. Families or groups, you should know both of those. I should have given a longer blank. And periodic table rows are called periods. Official unit of temperature measurement in the SI system is the Kelvin. And can we have a heterogeneous system made up of a homogeneous substance? Yes. As long as that substance exists in different phases, so we could have a pot with boiling water. That could be again a heterogeneous system because and steam. So we'll just be very clear that we mean it has some steam over it too. That could be a heterogeneous system is different in different places. In some places I have liquid water, in some places I have gaseous. But it's made up of a homogeneous substance because it's all made up of water. So yes, or the one I more commonly use that you guys probably remember, if you remember anything out of the class, is ice cubes, a glass of water with ice cubes in it. Okay, 10. Observation, hypothesis, theory, or law. So remember that these two things, hypothesis and theory, explain why something happens. So they're an explanation. A law is a statement of what happens, and an observation is something we can touch, taste, see, or feel. So my car won't start because, here's a trigger word. If you see because, it means it's either a hypothesis or a theory. It is explaining something. So then it's just how well tested it is. My car won't start because the battery must be dead. That's going to be a hypothesis. That isn't something that scientists have tested, a few thousand times minimal. Animals evolve in order to better adapt to their environment. It's explaining why animals evolve, and yet it's got a lot of evidence behind it. It's been well studied, so we'll call that a theory of evolution. Water is colorless. That's something I can see, so that's an observation. Two objects of mass will attract each other. That's a statement of what happens, not explaining why, so that would be a law. And again, atoms form chemical bonds because, there's that key word, they share or transfer electrons. That's pretty dang well studied, so I'm going to call that a theory. Next page. All members with groups with special names. Iodine is a halogen. Xenon is a noble gas. Gas. I don't know why I put an E on there. Barium is a alkaline earth metal. And cesium is an alkali metal. Okay. Substance composed of two or more elements chemically combined is a compound. Is oxygen a compound? No. because it only has one type of element. And as we just said in the previous question, it has to be 2 or more elements chemically combined. And the SI prefix that means 1,000 is kilo, 1/1000th is milli, 1/100th is centi. How many sig figs are in each of the following numbers? First one has decimal point, so only leading zeros don't count. There are none, so all of them count. There are 5. Here is a decimal with some leading zeros. Those don't count, so only these 4 do. Here's a number without a decimal. Without a decimal, it's the zeros in back of the non-zero digits that don't count, so these guys don't count, and we have 3 of them that do. And here there are no leading or trailing zeros, so everything again counts, and we're back to 5. Okay, calculate the following to the correct number of significant digits. So for the first one, I have 18.8451 for a raw answer. Now I have to round it. And for adding and subtracting, our solution is to round things to the least precise position. Here we're only precise down to the tenths. Here we're precise down to the 10,000ths. The tenths is less. We can only be precise to our tenths place there, so we'll round that to 18.8. Okay, 119 minus 1.4 is 117.6 as a round raw answer. Again, we're only precise down to the nearest ones place there. And so here we have to round it to the nearest 1, and so we'll have an answer of 118. For the bottom one, now we have multiplication and division, and in multiplication and division, well, we have multiplication, I guess, but in multiplication and division, we have to count the number of significant figures for each item, and then whichever one has less significant figures controls our answer. Here we have 2 sig figs, that 0 doesn't count. Here we have 3 sig figs, that 0 doesn't count. 2 is less, our answer has to be to 2 decimal places. So as a raw answer, I have 19.84, but I have to round that now to being only 2 significant digits. So I'm going to round that to this place. That's going to round to 20, but I need to somehow indicate that this 0 is significant. That's not just a placeholder. I have it significant down to the ones place. So I could do that by placing a decimal after it. I could also do it by placing a line above it. I could also do it by placing a line below it. All of those are different conventions. The most clear, the best one to use, in my opinion, is putting the decimal beneath it or putting it into scientific notation as like a 2.0 times 10 to the first, in which we then only show what decimals are significant. So any one of these four would be a sufficient response. Finally, we have, again, another problem with division. Same rule, we're going to count the number of sig figs. We have 3 here, we have 4 there, and so our answer needs to be rounded to only having 3 significant digits. And our raw answer is this big mess of a number of 49432.7, and we have to round that to having only 3 non-zero digits, 1, 2, 3, or 3 significant digits. Round it to that place. Since that's a 4, it's going to round down, and we will have this as 549,000. Okay, number 17 is something we didn't cover in class, but it was covered in the notes, so it is a legitimate fair game for the quiz. Well, I covered it a little bit in class, just kind of in the stream of talking in context of other problems when we started doing the counting atoms thing. We call a group of atoms that have a charge, or a single atom or group of atoms, an ion. If it's a group, it's a polyatomic ion. If it's a single, it's a monatomic ion. Again, we'll come back to that stuff in a little more depth in the future. We call them, if they have a positive charge, we call them a cation. And the way that I remember that personally is this little plus sign right here in the middle. That T in cation looks like a plus sign, positive. A negative charge is just an ion. It's an anion. Okay. 65 degrees Fahrenheit equal to what temperature in Celsius? So we're going to kind of flip back here to find our formulas, and we're going to say F equals 1.8 C plus 32. F equals 1.8 C plus 32. And now I've got a little bit of algebraic work to solve. I'm going to plug in what I know. I'm going to plug in the 65. So 65 equals 1.8 C plus 32. Again, if you have the other versions of the formula in your notes, you wouldn't have to necessarily do it this way, but this is a viable approach. So now I'm going to subtract 32 from each side. And I'm going to say that 33 equals 1.8 C. And then I'm going to divide by 1.8 on each side. And I'm going to say that C is 18.3 repeating degrees. We had 2 decimal places to start, so we run around to 2 decimal places in the end. Just kind of doing this really quickly and roughly. Actually, yeah, that would be right. 2 decimal places to end is 18 degrees Celsius. Okay. What about in Kelvin? Well, Kelvin is just Celsius plus 273, so we would have 291 Kelvin. And just add that 273 in on there. Oops, get those on screen. 291 Kelvin. Okay, same thing except going the other direction. This one's a little easier for the formula we're given. Fahrenheit equals 1.8 times that 22 plus 32. And so we can just crunch that into the calculator and find out that we would have a 71.6 rounded to the 2 significant digits. Sorry, I apologize about the bells. Obviously, I'm working from school, so I have no control over that. Anyway, rounded to 2 significant digits, we have 72 degrees Fahrenheit. In Kelvin, again, Kelvin is just Celsius plus 273. 273 plus 22 is 295 Kelvin. In what temperature? What is the temperature in Celsius at which all atomic motion would cease? That is absolute zero, negative 273 degrees Celsius. What is that temperature in Fahrenheit? So we're just going to go ahead and stick that back in our formula. Fahrenheit equals 1.8 times negative 273 plus 32. And again, just punch that through a calculator. And you find out that in Fahrenheit, it is negative 459 degrees Fahrenheit. It would be absolute zero. At what temperature does water freeze in Celsius? At 0 degrees Celsius. Okay. In Kelvin, 273 Kelvin. Again, water freezes at 0, boils at 100. In the Celsius scale. Okay. Solid has a density of 3.2 grams per cubic centimeter. How much does a 33 centimeter sample mass is this? Density equals mass divided by volume formula. We're going to substitute in what we know. 3.2 equals the mass divided by 33. And we'll end up with 33 times 3.2. And we'll end up with this mass equaling 105.6. But now we had only 2 sig figs to start, 2 sig figs there, 2 sig figs there. So we should have only 2 sig figs in our answer. So our mass is going to be 110 grams. Rounded to 2 significant digits. Kind of the other way you could do this one is just looking at the unit analysis. If I've got some again, 3.2 grams over 1 cubic centimeter. To get that rid of that cubic centimeter and get down to just grams, which is the measure of mass, I could just multiply by the 33 cubic centimeters, and unit-wise, those would cancel, and I'd end up with the same 3.2 times 33. So whichever one of those ways makes more sense to you, you are welcome to use either. They both arrive at the same solution. Again, density equals mass divided by volume. We have here some mass. Our formula, again, density equals mass divided by volume. We have here a mass of 74.35. We have a volume of 54. And that leads us to a density of 1.37685. And here we have 4 sig figs. Here we have 2 sig figs. This is dividing, so the 2 sig figs controls. And we need to round that to 1.4, and that is a gram per milliliter unit. It was grams in the top and milliliters in the bottom. Okay, to explain the difference between a theory and a law, that's pretty easy. Theories explain how or why, and a law states what happens in nature. So laws don't explain, they don't say because, they don't say any sort of explanation. It's just a statement of fact, a statement of what happens. Okay. What type of bond do metals and nonmetals tend to form? That would be an ionic bond. 650 feet into kilometers. So we'd have 650 feet, and we can tackle this a number of ways. Let's go back and look at our little conversion box and see what we've gotten. We've got a whole bunch of different stuff to pick from here. I'm going to use this one here. That 1 kilometer is 0.62137 miles. So 1 kilometer equals 0.62. Oh, no, I forgot it. 137. 62137. 0.62137 miles. Okay. There we go. So just jotting that fact down out of our little box there. I'm going to convert these feet into miles by knowing that there are 5,280 feet to 1 mile. And that gets rid of my feet, gets me into miles. And then I want to get rid of my miles and get into kilometers, and that's where this 1 to 0.62137 comes in. Of course, if you didn't know this conversion from feet to miles, you could have gone, from feet to inches, inches to centimeters, centimeters to meters, meters to kilometers. There's a number of ways you could solve this using the conversion factors that I've both asked you to memorize and provided for you on this document. So whatever kind of path you view is easiest, they all get to the same answer in the end. And that answer in this case would be some 0.1981 kilometers. Rounding to significant figures, again, in any unit conversion, however many we started with, we should end with. This number has 2 sig figs in it, so our answer should have 2. So we would round that to 0.20 kilometers. And we do need to keep that 0 because that is our second significant digit. Rolling onwards. Almost done. A couple pages. Okay, convert 1 kilogram per cubic meter to pounds per cubic inch. Okay, I've got a couple of conversions to make here. So I've got 1 kilogram over 1 cubic meter. And in my solution map, I need to go from kilograms to pounds. That's pretty easy. And then I need to go from cubic meters to cubic inches. And that one's maybe a little tougher. Neither of these are too bad. So I am going to say, again, go back to this box full of kind of conversions that I'm given here. And I'm going to say that 1 kilogram is 2.204623 pounds. 1 kilogram is equal to 2.20 And I don't even need to carry it further there. I could, I probably should, just for the example. So let me make sure I know what that is. I think it's 0623, but let's look again. 04623. 04623. I could have retained just these 3 digits, recognizing that I only had one significant digit to start, and so those other ones are going to chase far enough down in the decimal places that they'd get rounded out anyway. But the better procedure is just to use the full amount if you're at all unsure. So this now is going to take care of my first solution map. Or first step. That gets me out of kilograms and into pounds. Now I just got to get this cubic meters into cubic inches. And I can say, again, coming back to this little table, I can say that, which one do I want to use? Oh, there's one particular one that I was hoping to use, and I didn't. There we go. 1 foot equals 0.3048 meters. So again, 1 foot equals 0.3048 meters. And so I'm going to convert this meters into feet. Now, since meters were in the bottom, they need to be in the top. Feet need to be in the bottom. 1 to 0.3048. But now, since this is cubed, this needs to be cubed. And that gets me into cubic feet. And then I want to get to cubic inches, so I've got to get rid of feet, and I've got to go 2 inches. 1 foot is 12 inches. And again, because these were cubed feet, this needs to be cubed, which means I also have to cube the bottom. And that giant mess now will be only labels left. Kilograms cancel. Oops, sorry, pounds do not cancel. Meters cancel, cubic meters cancel, cubic feet cancel, and I have cubic inches, pounds per cubic inch. Perfect. So I'm just going to take that through the calculator and see what it yields. And this should be some 0.00036. Again, we only had one sig fig, so 0.00004 pounds per cubic inch. Okay. All right. Objects that occupy space have mass are considered matter. In our universe, other than the matter, there are only 2 other things, and they are space and energy. If I can see it without tools, it's macroscopic. And if I need tools to see it, it's microscopic. Only one letter different, but an entirely different meaning. Okay. If I take an atom down to, or an element down to the smallest particle, by fundamental, I mean, what is the smallest particle of an element that still has the attributes of that element? And that would be an atom. If I break down past the atom, I get into protons, neutrons, electrons. Those don't retain the chemical properties of the substance that they came from, so they are not fundamental particles. Well, okay, so they are fundamental particles. They're not fundamental particles of an element because then they've lost that identity as the element. Similarly, for a compound, we could say a molecule is the smallest that we can cut a compound into and still have it retain the chemical and physical properties of that compound. Okay, an example of a molecular compound is any combination of nonmetals. Now, I know you don't know necessarily what nonmetals would bond together and in what proportion, so I'm not going to judge it for correctness on that. All you would need to do is have 2 nonmetals to be considered correct. On an ionic compound, we need a metal and a nonmetal. Again, I don't care what ones you pick or how many of each you say are present, since we haven't learned that stuff yet. Just picking out that there's a metal and a nonmetal. 2 categories of pure substances we study are elements and compounds. Okay, what do we call a homogeneous part of a system that is separated from the rest of the system by a physical boundary? We call that a phase. That'd be like a ice cube floating in a glass of water. They are in two different phases. We could call it a phase boundary. A phase. 4 techniques for physically separating mixtures. Let's see, we discussed using a magnet. We discussed using a filter. We discussed distillation. What else did? And flotation. Yeah, that's the other one. Flotation. Another kind of simple unit conversion here, 43 cubic centimeters. And we know that for 2.54 centimeters, there is 1 inch. That's in that front box, if you haven't memorized it, like I have. And then we got a cube, both top and bottom, since that was cubed. And we will end up with 2.62 cubic inches. Again, now rounding to our 2 significant digits, 2.6 cubic inches. What element comprises most of the Earth's crust? Oxygen does, actually. What about your body? Also oxygen, because oxygen is the major component of water by mass. And since you are made up by mass, since you are made up mainly of water, that means that you are made up mainly of oxygen. You have more oxygen in your body than any other element. By far, actually. Considerably. By mass, not by number. By number, you have more hydrogen inside of you than oxygen, but when we talk about abundances, we're pretty much normally talking about mass abundance. Okay. Tell whether the following substances are likely metals or likely non-metals. So if I strike it and it makes a ringing sound, that is sonorous. That is normally a metal. If I try to bend it and it breaks, that means it is brittle and non-malleable, so that would be a non-metal. That is very light for its volume. That is an attribute of non-metals, being low density, light in any particular volume. It is shiny. Typically, metals are shiny. I use it to protect my hands from a hot pan. It's probably a non-metal because non-metals make better insulators. Metals are good conductors of heat and electricity, and of course you wouldn't want a good conductor because you don't want it getting to your hands. I point a hair dryer at it and it melts. That is also typically a non-metal. Non-metals tend to have low melting and boiling points. A homogeneous mixture of metals is called an alloy. To the right of the staircase are the nonmetals. I suppose I'll write that out, nonmetals. In the short part of the periodic table are the transition elements or transition metals. In the tall part are the main group elements. And then a few more unit conversions, 10 meters per second, and I want to get that into feet per hour, so I can say there are 3,600 seconds in 1 hour. That takes care of getting the bottoms into hours, and I can say that there are 0.3048 meters in 1 foot, and that gets the meters converted to feet, so I'll have feet in the top, hours in the bottom. I am golden. And we end up with this big mess of a number, 118,110. But here I only had 1 sig fig, so I have to round this to 1 sig fig. So I'm going to round that to 100,000 feet per hour. Okay, in this case, 30 gallons. And I want to convert those to liters. I'm going to come back here and I'm going to find something that allows me to work between gallons and liters. Here I've got gallons to quarts, and here I've got quarts to liters. So that'll do it. 1 liter is 1.0567. 567 quarts per liter. And, sorry, get that back on screen. 30 gallons. There in 1 gallon are 4 quarts. And for each 1 quart, each 1.0567 quarts, there is 1 liter. That'll get me to liters. So I end up with this 113.6. Again, 1 sig fig. So I got to round it to 1 sig fig. So I would have 100 liters approximately in 30 gallons. Okay, now I've got 1.75 tons to milligrams. I have 1.75 tons. There are in 1 ton 2,000 pounds. There are in 1 pound 454 grams. And you can look these up in that front table. And in 1 gram, there are 1,000 milligrams. And therefore, I just need to multiply everything on the top. And I'm going to end up with a ungodly large number. And that is okay. I'm going to put it in scientific notation just to make it a little easier to write. So I'd have 1.589 times 10 to the 9th. Again, I had 3 sig figs, so I want to round this to 3 sig figs. So I have 1.59 times 10 to the 9th, and that is milligrams. Okay. And that's it. So that is all the questions on the review. Hopefully that helps you kind of grease the wheels a little bit, get prepared for our test that is coming up on Wednesday. If you have any other questions, comments, or concerns, please feel free to contact me. I am always more than willing to help. Furthermore, there is a review PowerPoint that I've also mounted onto Teams. You hopefully have encountered that already. If you feel the need for a little extra practice, go ahead and hit that up. Other than that, have yourselves a great day. I will be holding class tomorrow in the previously discussed time frame, so if you have any other questions and you don't necessarily feel like they're worthy of making a separate appointment or a separate message to me, just show up for class and we can address anything then. Other than that, hope you're having a great day. Hope to see you guys soon. It's only been 1 day and I'm already tired of virtual. So I want you guys back in my classroom and I hope we get to do that soon. Have a great day.